Welcome guys, this is going to be the first video for Lib Academy. Now today I'm going to be going over some biochemistry. I am following the Okan curriculum, so whatever they teach us in Okan is what I will be explaining. Today we're going to go over the properties of water, which is the first week of October lecture, our first biochem lecture. This is the basics, but it is really important to understand the basics and why water is such an important element in biochemistry. Well, first, majority of chemical reactions actually exist in water. Water is the natural solvent, and thanks to water, these reactions can follow a specific pathway, uh, and it also helps determine the final structure of a reaction. So water is going to help us determine the final structure of reactions in biochemistry. So the first property I want to go over is, why is water a polar molecule? So first let's look at, one second here, let's see, so let's draw the hydrogen, and let's go back. Alright, so let's look at the periodic table here. This is the electronegativity trend. So electronegativity increases from left to right and from bottom to up. Okay, so we know that fluorine is going to be the most electron negative element. Now you might ask, why is helium or neon not more electronegative? Well, this is because they are noble gases. They already have a full valence shell of electrons. And as we know, electronegativity is the ability to gain and attract electrons. So now that we understand that, let's move on to H2O. Why is H2O polar? So first, let's look at its structure. H2O is not a linear molecule. As we can tell, there is an angle. It is asymmetrical. It has a bent shape. So, as we also know, oxygen is much larger and more electron negative than hydrogen. So, it is going to pull the electron density towards it. This causes oxygen to become partially negative and hydrogen becoming partially positive, partially positive. The difference of charges between hydrogen and oxygen will cause an electron dipole moment, and we went over this in physics as well. It's going to be electron dipole moment going this way. Therefore, your net dipole moment is going to go in this direction. So this is just a very basic explanation of why H2O is important in biochemistry and why it is polar. Again, it is due to its asymmetrical bent shape and the difference of electronegativity between the atoms, which is hydrogen and oxygen. Alright, so for the second water property is going to be the intermolecular bonding, in this case hydrogen bonds. So first of all, do not get confused between intermolecular and and intramolecular bonding. Inter and intra are completely different and they're easily confused. So intermolecular is going to be a bond between two compounds, between two waters. This is intermolecular bonding, and intra is going to be between atoms, which forms the compound, which forms the molecule. So let's discuss hydrogen bonding. Anytime a hydrogen bonds with a partially negative atom, it is going to be a hydrogen bond. Remember this. Hydrogen bonds are very strong intermolecular bonds. And what makes them so strong? What makes them special? It is because hydrogen is the smallest atom found in nature. So, since hydrogen is so small, it can actually get very close to oxygen, causing a very strong bond due to the force. So let's take a look at the equation quickly. So you have force 1 over distance squared, and we know that the force is going to be inversely proportional to distance. So as distance decreases, force increases, and vice versa. As distance increases, force decreases. So in this case, we know that hydrogen is very small, which causes the force to become very large and very strong. So H2 molecules attract strongly to other H2 molecules via electronegative forces. Keep this in mind, very important. All right, so let's look at the final water property being the hydrophobic effect. So when looking back at the first and second property, first being that water is polar, and second being that water has intermolecular bonds, specifically hydrogen bonds, which are very strong, as you guys remember. This all leads and manifests the hydrophobic effect. So let's take, for example, a polar compound when put into water. In this case, we're going to look at NaCl, sodium chloride. So, sodium chloride has an ionic bond where sodium actually gives away one full electron from its valence shell to chlorine. This causes an ionic bond. We'll go over ionic bonds and covalent bonds and polar covalent, nonpolar covalent later on in this video. But for now, let's get into the hydrophobic effect. So, when placing sodium chloride into H2O, the ionic bond breaks. The hydrogen then in H2O, the hydrogens in the H2O will form bonds between sodium and chlorine separately. So you have bonds that are created separately after the breaking of the ionic bond. You have this being positive, this being negative, and this being positive. Therefore, you have more hydrogen bonds. And by placing a polar compound into H2O, H2O will dissociate that polar compound and dissolve the polar substance thanks to hydrogen bonds. And more hydrogen bonds equal a favorable reaction. Make sure you remember this. The more hydrogen bonds equal a favorable reaction. Alright, so what happens if we place a nonpolar molecule into water? So, as we know, nonpolar molecules have a symmetrical charge distribution, and also nonpolar molecules do not have an uneven charge distribution. They cannot form hydrogen bonds because they have an even charge distribution. So, for example, as you can see here, when you place the nonpolar molecule into water, the water molecules form a cage around this right here. They form a cage around this nonpolar compound. This is not stable, and H2O becomes trapped around the nonpolar molecule. Now, what is the big issue here? Is once H2O is trapped, it cannot create hydrogen bonds between each other. So not only can you not create hydrogen bonds with the nonpolar compound, being trapped restricts them from creating hydrogen bonds between each other. Therefore, this is a non-favorable reaction. As you remember, putting sodium chloride into H2O, a polar compound, created more hydrogen bonds, which became a favorable reaction. In this case, we are restricting hydrogen bonds, which is a non-favorable reaction. Finally, let's discuss what happens if we place two nonpolar molecules into water. Same thing at first. The H2O is going to get trapped around, as seen right here. 1 second here. As seen right here. Same as before. The H2O is going to get trapped around the polar substance and is going to be a non-favorable reaction. However, if the two nonpolar compounds aggregate, it will form hydrogen bonds. Now, how does it do that? If the two nonpolar compounds aggregate, less water is trapped. So when they aggregate as in combine, the waters here that were here are released. They're not trapped anymore, and they can form hydrogen bonds. This is a favorable reaction. Since we decrease the number of trapped water molecules, they can form stable hydrogen bonds. So the interaction between the nonpolar molecules, this right here, the interaction between the nonpolar molecules in a polar solvent, water, is known as the hydrophobic effect. The hydrophobic interaction causes the hydrophobic effect. Again, these waters are not trapped anymore, and they can form hydrogen bonds and stable hydrogen bonds.